Welcome, my dear students, to Standard 10th class, Science and Technology, Part 1. We continue with the chapter Heat. Dew point and humidity. About 71% of the earth is covered with water. Due to constant evaporation of water, water vapor is always present in the atmosphere. The amount of water vapor in the atmosphere help us to understand the state of daily weather. The presence of water vapor in the air makes it moist. The moisture in the atmosphere is called humidity. For a given volume of air at a specific temperature, there is a limit on how much water vapor the air can contain. If the amount exceeds this limit, the excess water vapor converts into water droplets. When the air contains maximum possible water vapor, it is said to be saturated with vapor at that temperature. The amount of vapor needed to saturate the air depends on the temperature of the air. If air temperature is low, it will need less vapor to saturate the air. For example, if the temperature of air is 40 degrees Celsius, it can contain 49 grams of water vapor per kilogram of dry air without condensation. If the amount of vapor exceeds this limit, the additional water vapor will condense. However, if the temperature of the air is 20 degrees Celsius, it can contain only 14.7 grams of water vapor per kilogram of dry air without condensing. If the vapor contained in the air is less than the maximum limit, then the air is said to be unsaturated. Suppose unsaturated air at a certain temperature is taken and its temperature is decreased, a temperature is reached at which the air becomes saturated with vapor. This temperature is called as the dew point temperature. The vapor contained in the air is measured using a physical quantity called absolute humidity. The mass of the vapor present in the unit volume of air is called absolute humidity. Generally, absolute humidity is measured in kilogram per cubic meter. The feeling of humid or dry nature of air not only depends on the amount of vapor in the air, but also depends on the how close that amount is for making the air saturated with the vapor. It means that it depends on temperature of air also. Percent relative humidity is given as actual mass of water vapor contained in the air in a given volume upon mass of the vapor needed to make the air saturated in that volume into 100. The relative humidity at the dew point is 100%. If the relative humidity is more than 60%, we feel that the air is humid or moist. If the relative humidity is less than 60%, we feel that the air is dry. During winter season, you may have observed a white trail at the back of a flying plane in a clear sky. As the plane flies, the vapor released by the aeroplane engine condenses and forms clouds. If the surrounding air is having more relative humidity, it takes a long time for the white trail formed by condensation of the water vapor to disappear. If the relative humidity of the surrounding air is less, either the size of the white trail may be small or it may not appear. Take a bottle of cold water out of a refrigerator and keep it outside for a while. Observe the outer surface of the bottle. Drops of water can be observed on the outer surface of the bottle. In the same way, if we observe the leaves of plants or grass or window glass of a vehicle, early in the morning, we see water droplets collected on the surface. Through these two observations, we sense the presence of water vapor in the atmosphere. When air cools due to decrease in temperature, it becomes saturated with water vapor. As a result, the excess water vapor gets converted into tiny droplets of water. The dew point temperature is decided by the amount of vapor in the air. Unit of heat. The units of heat are joule in SI units and calorie in CGS units. The amount of heat necessary to raise a temperature of 1 gram of water by 1 degree Celsius, that is from 14.5 degrees Celsius to 15.5 degrees Celsius, is called as 1 calorie heat. Similarly, the amount of heat necessary to raise the temperature of 1 kg of water by 1 degree Celsius from 14.5 to 15.5 degrees Celsius is called as 1 kilocalorie heat. It is clear from this that 1 kilocalorie is equal to 1000 calorie. Specific heat capacity. We will try to understand specific heat capacity with the help of this experiment. A tray with thick layer of wax is taken. Solid spheres of iron, lead and copper of equal mass, burner or spirit lamp and a large beaker is taken. Take 3 spheres of iron, copper and lead of equal mass. Put all the 3 spheres in boiling water in the beaker for some time. Take the 3 spheres out of the water. All the 3 spheres will be at the temperature of 100 degrees Celsius. Put them immediately on the thick slab of wax. Note the depth that each of the sphere goes into the wax. The sphere which absorbs more heat from the water will give more heat to the wax. More wax will thus melt and the sphere will go deeper in the wax. It is observed that the iron sphere goes deepest into the wax. Lead sphere goes the least and copper sphere goes to intermediate depth. This shows that for equal rise in temperature, the 3 spheres have absorbed different amounts of heat. This means that the property which determines the amount of heat absorbed by a sphere is different for all the 3 spheres. This property is called as specific heat capacity. It defines as the amount of heat required to raise the temperature of unit mass of an object, for example 1 kg, by 1 degree Celsius is called as the specific heat of that object. The specific heat capacity is denoted by small letter C. The SI unit of specific heat is joule per degree Celsius kg and the CGS unit is calorie per gram degree Celsius. Substances and their specific heat is given. Water has 1 calorie per gram degree Celsius specific heat. Paraffin has 0.54 calorie per gram degree Celsius specific heat, whereas kerosene 0.52 calorie per gram degree Celsius specific heat. Aluminium has 0.215 calorie per gram degree Celsius. If the specific heat of an object is small c, the mass of the object is given as small m, and if the temperature of the object is raised by delta T degree Celsius, the heat absorbed by the object Q is given as m into C into delta T. In the same way, if the specific heat of the object is small c, the mass of the object is small m, and if the temperature of the object is decreased by delta T degrees Celsius, then the heat lost by the object is given by Q is equal to m into C into delta T, where delta T is the difference in the temperature of the object. Heat exchange. If heat is exchanged between a hot and a cold object, the temperature of the cold object goes on increasing due to gain of energy, and the temperature of the hot object goes on decreasing due to loss of energy. The change in temperature continues till the temperatures of both the objects attain the same value. In this process, the cold object gains heat energy and the hot object loses heat energy. If the system of both the objects is isolated as shown in the figure from the environment by keeping it inside the heat resistant box, meaning that the energy exchange takes place between the two objects only, then no energy can flow from inside the box or come into the box. In this situation, we have the principle as heat energy lost by the hot object is equal to heat energy gained by the cold object. This is called as the principle of heat exchange. Measurement of specific heat by the mixing method and calorimeter. The specific heat of an object can be measured by using the mixing method. For this, calorimeter is used. Calorimeter you have learned in the previous standard. If a hot solid object is put in the water in the calorimeter, heat exchange between the hot object and the water and the calorimeter begins. This continues till the temperatures of the solid object, water and the calorimeter becomes equal. Therefore, we have the relation as heat lost by the solid object is equal to heat gained by the water in the calorimeter plus heat gained by the calorimeter. Here, heat lost by the solid object is given by Q is equal to mass of the solid object into its specific heat into decrease in temperature. Similarly, heat gained by the water in the calorimeter is given by Q1, that is equal to mass of the water into its specific heat into increase in its temperature. Heat gained by the calorimeter Q2 is given by mass of the calorimeter into its specific heat into increase in its temperature. Therefore, we have heat lost by the hot object is equal to heat gained by the calorimeter plus heat gained by the water. Therefore, we have Q is equal to Q1 plus Q2. Using these equations, if the specific heat of water and the calorimeter are known, we can find out the specific heat of the solid object. Thank you.